Hello everyone, welcome to our presentation on the short ROV. We are the beach buoys. To my left we have Jason, Sam, Eric, Raul, and myself, Mike. We have been called upon by BP to create an ROV that fits within the requirements of a 15-kilogram mass. It will fit inside of a box that you can use for transfer. It has a full range of motion. The cameras and thrusters are completely protected by the frame. It's controlled by a control box which is attached by a tether, as well as having a minimum speed of 0.5 meters per second. Now my colleague Jason will take over with the design of the beach.
Alright, so some materials we use when building our ROV include a PVC pipe connected by PVC cement, and to secure different components we use hose clamps as well as zip ties, and for the electronics we have thrusters connected to a control box via tether, and in addition we had, for buoyancy we had buoys and duct tape encased foam, and for ballast we had adjustable lead ballast. So in our approach to our design, we wanted it to be as minimalistic as possible. So inside the frame, we have space for basically the canisters as well as the thrusters. In the front, we have a high surface area arm, which is used to complete the task of the competition. It's very mobile with thrusters in all 4 directions, as well as the ability to adapt the thruster positioning for speed or maneuverability. And we have adjustable ballast and buoyancy for the day of the competition. This is a picture of our 3D model. As you can see the dimensions, it's fairly thin and high. And this is an image of our final product. As you can see, our camera is attached to the frame at the top. We have a detachable arm in the front. Buoy secured to the top for maximum stability. And our canister is zip tied straight to our frame. We have our side-to-side thruster there for horizontal motion. Our 2 back thrusters for speed. And our tether attachment ring at the very bottom frame, and a foam block underneath the canister for increased buoyancy, and adjustable ballast, which are pieces of lead attached to a zip tie. And at the very top of the frame, we have an up and down thruster. Now, my colleague Sam will talk about design.
Okay, so what we wanted to do was make sure that this met the requirements, and this was influenced by our initial research as well. And you can see we chose a design that fits very tightly around the canister and has a rigid frame and thrusters in every direction so that it has a full range of motion. And the center of buoyancy is significantly higher than the center of gravity, which allows it to have good stability. For the structure, we wanted a rectangular prism that was durable and rigid and had a floatable PVC frame, so there weren't many differences in buoyancy based on air bubbles. It's also within BP's size and weight limits. For the control box description, on top we had 2 sets of buttons for forward and backwards, and we also had a left and right single pole double throw switch and an up and down one to control it. And all of these were wired in parallel, which means they can be operated independently and designed like a game controller to be ergonomic and easy to use. For the thruster placement, the goal is to maximize both speed and maneuverability, so we had 2 configurations. One was with all 4 thrusters pointing backwards, and one was with 2 thrusters pointing backwards, 1 up and down and 1 side to side. And this allowed us to have both configurations for speed and maneuverability. And the thrusters were placed towards the rear of the ROV to minimize turbulence. You can see images of it. On the left, we have the 4 thrusters backwards, and on the right, we have 2 thrusters backwards. As for the camera placement, it was placed in the front and within the frame and near the top, so it had a full field of view. And there were no obstructions, and had an adaptable PVC mount with a zip tie, so both camera types could fit easily. Here's our mass budget. You can see the payload was the heaviest at about 5.5 kilograms, and the frame was the next heaviest, about 1.5 kilograms, and it came in at about 9 kilograms, which is still under BP's weight limit. And now Eric will talk about performance.
We did initial testing in the GFL lab. We noticed that all our thrusters functioned correctly and gave us a full range of 6-direction movement. We also performed 5 speed tests in the tank there with an average speed of 0.554 meters per second, which meets BP's requirements. Here so you can see a graph of our 5 trials, with the purple line here being the average speed of 0.554. We first anticipated our top speed using a coefficient of drag of 1 in this equation here. The coefficient of drag was approximated based on the shape of our ROV and prior research done before building. Here you can see the 2 values for our different configurations. This is the calculation for thrust for all of our different thrusters. We chose the 2 most powerful thrusters to go in the backwards direction to provide the most speed in the forward direction. The actual top speed was calculated and found out at the YMCA, doing 3 trials in a 15-meter pool, 15-yard pool. Our first trial was the fastest with 0.599 meters per second. The second one was a little bit slower as we hit another ROV that was in our lane, went 0.536 meters per second. The third trial of 0.277 meters per second was because we were driving the opposite direction and our driver had some trouble adjusting to that controls. Average max speed using the 2 good trials calculated to be 0.566 meters per second. Using this top speed, we recalculated our coefficient of drag to be 5.3. This seems very high, but considering the tether is pulling on the ROV, it fits our data. Now Rahul will talk about our experimental research.
So to calculate the center of gravity, we took the weight of each of the individual components and multiplied it by the distance from the origin in the x, y, and z directions respectively. As you can see, with this, we set the origin at the bottom center of the ROV, and by finding the moments about each of these axes, we then divided by the total weight of the ROV to find the center of mass in 3 space. As you can see, it's roughly symmetric about the x-axis. It is slightly towards the front of the ROV, the y-axis, and about a third of the way up in the z-axis. The center of buoyancy was calculated in a similar fashion, except we used volume instead of weight. In this case, we used SolidWorks to help us out because we found that estimating the volume of each of the individual components was quite difficult to do. So we calculate the center of mass at uniform density to estimate the center of buoyancy. And we found that it was roughly the same in the x and y directions, but it was about 7 centimeters higher in the z direction. And with the center of buoyancy being so much higher than the center of gravity, we believed our ROV would be stable. We tested this initial stability in GFL by turning our ROV 90 degrees, and we found that it righted itself, so this confirmed our initial stability analysis. Just to give you a visual representation, this is the red dot represents center of buoyancy, the blue dot represents center of gravity. As you can see, they're about the same in the x and y, but the center of buoyancy is significantly higher than the center of gravity, which makes us believe that our ROV would be stable. As far as competition procedures go, the first step was just to get everything secure, so attach the canister and the camera. Then we divided into different roles based on, as you can see here, based on our different team members. And then we actually had to get into the water and complete the task of opening the valve, reading the data, and then closing the valve. During the competition, we had 2 qualifying trials. Our first run was slightly slower because we were still adjusting to the course and getting used to it. Our second run was actually the fastest run in the competition. We had a time of 3:16.6. And just in both trials, we encountered some difficulties. One was communication between team members. We found that was quite difficult. And adjusting the ballast and buoy material, we found that was quite difficult throughout the 10 minutes. And just in maneuverability as a whole, we found that with our maneuverability configuration during this competition, the ROV had a full range of motion. We found that the high surface area arm was very effective in staying on the valve paddles and pushing them effectively. We found that the side-to-side thruster and the small design allowed us to turn 360 degrees quite quickly after pushing the valves. And we found that one problem was that it was somewhat hard to read data because we weren't neutrally buoyant and the limited time to adjust the buoy material was not enough time to do that. Now Mike will talk about product development.
So to take our prototype into a real-world design, we had to first think about scaling. BP has given us a scaling factor of 2.5 as shown there. And if we apply this scaling factor using this equation to our dimensions, we can come up with view dimensions of 47 centimeters by 86 centimeters by 110 centimeters. We can also apply a similar formula to recalculate the center of gravity and center of buoyancy. And based on the numbers given here, we see a similar stability as our model. Now, if we take into account also we have to scale up the velocity by using Reynolds scaling. If we use this formula shown here, we get a new velocity of our full-scale model being 0.155 meters per second. Now this seems a little bit slow, however we also would like to scale up the power, and we did so using this equation, which would give us a new effective power of 109.44 watts, as well as a full-scale braking power of 536.53 watts. Now taking all these numbers into account, we can actually look at the operation in the Gulf of Mexico. If we look at the operation, we can see possible troubles that we will run into, for example, warm water temperatures, the shallow water, and wildlife. After we look at these different problems, we come up with a few recommendations that we would like to give to you as examples so that you can change a few things in this real-world design. For example, carbon fiber frame, it's durable and has a very similar density as PVC, as well as using steel cables instead of zip ties that tie things down. Furthermore, we'd like to affect the tether. If we use a winch system and neutrally buoyant tether, we can minimize tangling and the effect of the tether on the CG. Also, as said before, we'd like to scale up the power, increase the battery size, or look at different options for thrusters, blades, or orientation. Another thing that we thought was a problem for our prototype was the actual camera. It had a very small field of view. We'd like to increase it to 180 degrees and increase the lighting on it. Furthermore, if we had to do it all again, start back with a prototype, one thing that we would definitely change is we would take into account our drag. As you can see here with an F-16 or this ROV, they had a very different front than our very flat surface. We would like to reduce the coefficient of drag down to something in between 0.42 and 0.5. And now we'd like to open this time up for questions.
So, what sort of system would you put in place to switch between the speed and the maneuverability configuration if you were to like use it in the real world?
So what we had is we had an adjustable PVC piece that could be secured with a zip tie. It had two orientations. In the real world, this could be motorized. It could be put on a servo or something like that to make it easier to use.
Okay, so you showed the picture of your controller. You had labels for 2 of the buttons on the front side of it. What on earth are the other 2 buttons for?
One's in the back, that's the.
No, on the left side.
Okay, yeah, so, same thing, just opposite thruster. We had 2 thrusters pointed back in our maneuverability design. Obviously, the right side was for the right thruster, and the left side was for the left thruster.
With the idea being like you activate one and it will turn slightly.
Yeah, yeah.
Okay.
I noticed there was like a large difference between the coefficient of drag. Because I was like, I tried to miss that in your presentation. Why was there a big difference between estimated action?
Yeah, so our frame ended up being a little bit closed off based on the big payload and our thrusters right there, and also the tether dragging on the back of the ROV also produced a lot of drag that we had to take into account when we're doing the full scale changes to the neutrally point and such to the winch system as well.
Yes.
So the setup of your ROV, most other ROVs we saw at the competition were more of a square and that were long. Why'd you go with the vertical rectangle? How'd you decide upon that?
Okay, so one of the things we looked at was just minimalistic. We built it pretty much around the canister, and we wanted enough room to put the canister in and not hit the thrusters, because the thrusters were on the whole time. And by doing this, we made it end up being like tall, long. Seemed to work, however, but we'll talk more about it in the final report.
Additionally, with the tall height, we have a high center of buoyancy compared to our center of gravity, which we thought would make it stable.
And kind of the shape of the box was like kind of tapering outward, so this design allowed us to put more things at the top end points.
Yeah, I gotta go back to one from grading. How did you said you calculated your coefficient and drag from the speed test data. How did you do it again? I didn't have a chance to write it down. I know you
So
did it.
we assumed that the drag force is equal to the thrust as in the top speed calculation, and then solved for a coefficient of drag using the velocity for our max speed calculation, which was 0.566 meters per second.
That you got at the trial.
Yeah.
Right, okay, cool, thank you. Okay, thanks very much.